Minasan, konnichiwa. Zamurai Engineer this. In this video, we will be discussing another type of functions. Group of functions wherein there is a distinct individual characteristic. We call discrete functions. On the previous module, we already discussed about the continuous function, how to differentiate. Differentiation of continuous functions. Now, we would like to do the differentiation or taking of derivatives of discrete functions. Let us continue. So, there are three different methods that we apply in our differentiation of function in terms of numerical methods. So meaning we would like to estimate the derivative of a function with acceptable level of tolerance. So we applied what? What are those that we applied previously? We applied the FDD, which stands for forward divided difference. We also applied BDD, backward divided difference, and CDD, central divided difference. So let us start with forward divided difference approximation method. But now we are dealing with a function which is discrete. What do we mean by discrete? Discrete is individually separate and distinct. For example, if you can look at the ends of my fingers, the ends of my fingers could represent a curve. It is a curve like this. Okay, it's a curve. If these 5 points, 1, 2, 3, 4, 5 points represents a curve, we can still study it. We can still analyze it. We can evaluate it. However, this curve is not a continuous function. It's not a continuous curve because one point is separated from the others. They are individually distinct from one another. What is the value of this function at this point? This is the value, this height. What is the value of this function at this point? This is another value, different from one another. But they are not continuous. This type of function, if you are just looking at the ends of my fingers, that is what we call discrete function. In contrast, we have, for example, a continuous function that we already discussed. For example, I have here the line, the rope, okay, the tie. This tie is a continuous function because there is no break. There is no individuality between the points lying on the curve. Okay, so that is the difference between discrete function and continuous function. It is easier to handle continuous function when we are talking of calculus because calculus requires as a condition the function to be continuous and the derivative should exist. Okay. However, we can still do the analysis and finally the approximation with regards to discrete function. Let us again recall that the definition of derivative is equal to fx plus delta x minus fx over delta x as x approaches 0. We took this limit. Okay, so trying to take this limit as delta x approaches 0, and we already explained that for a finite value of delta x, we can choose delta x to be as small as possible, but we cannot choose delta x to be 0. Because in mathematics, division by 0 is not permissible. So what we're going to do, we choose delta x to be very, very small. Okay? Negligible value, but still, it has a value. Okay, and we evaluate what? Fx plus delta x minus fx over delta x to be the approximation of the derivative definition. Similarly, we can use this general concept of approximation to discrete function. So let us take a look at our popular graphical representation of an example curve. So we have the curve, and as you can see, there are two important points in order to define a slope. X and x plus delta x are the 2 points that could allow us to calculate slope and become an estimate of our derivative. Because as you know, again, I would like to remind everybody that the derivative is slope in physical terms. So, and from this diagram, you will notice that this is really a forward difference because x is an important point that we would like to know the slope, and we add another point which is forwardly looking point, that is x plus delta x. Okay, so forward meaning the x value increased by a little bit, by a small amount. So we need that another point in order to evaluate slope without without breaking any mathematical rules. Example 1, the upward velocity of a rocket is given as a function of time in table 1. We have a given series of values of distance and series of values of time in the first column, and in the second column, the value for its velocity. Okay. So instead of giving an equation, because an equation characterizes a continuous function. An equation characterizes a continuous function. In tabulated representation like this, at time 0, the velocity is 0 meter per second. At time 10 seconds, the velocity is what? 227.04 meter per second. What is the velocity at time 20 seconds? That is 517.35 meter per second. What is the velocity at time 22.5 seconds? The velocity is 602.97 meter per second. It is clearly stated here that there is a discrete function. Discrete meaning it doesn't necessarily be integer. Discrete doesn't necessarily be an integer. Integer meaning there is no decimal point. What is the example of integer? 0, 10, 15, 20, and 30. 22.5 is not an integer because it has a decimal point. Okay? Clear? So, when we talk of discrete, it is almost similar to the integer, but discrete means they are individually separated from each other. They are distinct. So 0 and 10 are discrete, meaning this one. The value of velocity at 0 is 0. The value of velocity at 10 is 227. If you ask me, what is the value of velocity at 8 seconds? I cannot answer you. There is no value of velocity at 8 seconds. Because there is no assigned finger there. The fingers are 0. Take a look at the table. 0, 10 seconds, 15 seconds, 20 seconds, 22.5 seconds, and 30 seconds. So there are what? Six values. There are no values in between. If you ask me, what is the value of velocity at 17 seconds? There are none. There is no value of velocity at 17 seconds. Only at 15 seconds and 20 seconds and 22.5 seconds. That is the meaning of discrete function. Using forward difference approximation, find the acceleration of the rocket at 16 seconds. Okay, so let us do this. We still have to approximate. These are real life problems. Even if something like this would happen, you have to solve it. That is the difference between engineer and mathematician. Okay. So already you know the difference between mathematician and engineer. So if the mathematician would answer this, clearly the answer would be nothing. There is no solution for this. However, to find the acceleration at the time 16 seconds, we need to choose the two values close to 16 seconds. What are those values? Of course, 15 and 20, which are discrete. There is a value at 15 seconds. There is a value at 20 seconds. There is no value at 16 seconds. Okay, clear? This is a clear constructive example of the difference between mathematics and engineering. If you try to ask this in mathematical perspective, there is no answer to this. They would say, of course, we don't know. There is no value of the function at that point. This is similar to what would you expect in real life as an engineer. There is no perfect setting in the real world. Engineers should adapt to the reality of on the ground. What is the reality on the ground? Okay, you have to solve it, whatever it takes. So to evaluate it, the 2 points are, of course, 15 and 20. Okay, let us now have a concrete idea how to do it. Still, we know something from physics and mathematics. We will still use those. Okay, in order to what? Estimate. Yes, we have to estimate. Okay, we have to estimate. So acceleration is actually given by velocity at the forward point minus the velocity at our target point divided by the change in time. And we have what? We are going to use t is equal to 15, our target point, and the forward point is 20 seconds. So let us consider that, because those points is nearest, closest to what is required. The required is velocity at, or the acceleration at time 16 seconds. Okay, so what is the delta t right now? So 20 minus 15 is just 5 seconds. So continued. So therefore, since we know from the table, you already has a table given the velocity at 20 seconds and velocity at 15 seconds. So you have to divide it. So divide, subtract it from one another. So and then divide by delta t, which is we already calculated to be 5 seconds. So therefore, the answer of acceleration at 16 seconds is actually what? Approximately 30.914. That is an approximation. Our approximation as engineer. Okay? So, at least we have the answer. Unlike the mathematician that in mathematics, there is no rule that would lead us to any answer. Mathematician's answer would be, there's no solution. We cannot produce an answer in this type of question. And that is supposedly the answer. Now, direct fit polynomials. In this method, given n plus 1 data points, there are meaning n plus 1 coordinate system. No? Coordinate meaning x and y coordinate system. X, y, x, y, x, y, x, y, and so on. How many of them? N plus 1. One can fit nth order polynomial given by p sub n of x, function of x, no, is equal to a0 plus a1 x plus and so on plus an minus 1 x to the n minus 1 plus an x to the n. So there are how many terms? So there are n plus 1 terms. Okay. To find the first derivative, of course, it is easy matter for us to take the derivative of this, the derivative of p. So then is equal to a1 because derivative of 0, which is a constant, is 0. So a1 plus 2a sub 2x plus and so on plus coefficient n minus 1 a n minus 1 times x to the n minus 2 power plus n an x to the n minus 1. If you want to look for or find for higher derivatives, they can be found by just taking the derivative of this. How many times? For example, do you want the third derivative? So take the derivative of this given p sub n 3 times. If do you want the fifth derivative, so take the derivative of this 5 times. Okay, so that's all for direct fit polynomial representation. Meaning we would like an algebraic function to represent some curve. Okay, that is what we mean by giving out the representation p sub n. Okay, so the upward velocity of a rocket is given by the function time in table 2. So velocity as a function of time. So we have the given. Okay. So this is the same given as our example 1. Okay. And using the third order polynomial interpolant for velocity, find the acceleration of the rocket at 16 seconds. Okay. So third, using the third order polynomial. So let us solve this. So velocity using the direct fit representation. The first equation that you can see on your monitor, that is the direct fit polynomial representation. Since we want to find the velocity of time is equal to 16 seconds, we are using third order polynomial. We need to choose the 4 points closest to 16 seconds. So instead of 2 points closest to 16 seconds, we would like to find the 4 points instead. And also, in that also bracket, time is equal to 16 seconds. Bracket meaning 16 seconds is inside it, inside those points. Okay, to evaluate it. The 4 points are, of course, time 15 seconds and time 20 seconds, which we already used in the previous example number 1. And in addition, another points that are nearest to that is T10 seconds and T22.5 seconds. So all of the four. The difference is the method. In our example 1, we only use 2 points that bracketed the target time 16 seconds. Now we use 4. Okay, and when we use 4, the bracket manner is there are 2 points here and there are 2 points here. So there are a total of 4 points. Okay. Okay. So using this method, we can find out that velocity at 10, which is already given in the problem, can be represented by this direct fit polynomial. So also for velocity 15, velocity 20, and velocity 22.5. Take a look. For example, velocity 10. The value is 227.04 is equal to A0 plus A1 times 10. Because X is 10, that's why we substitute 10. And A2 times X squared, that is 10 squared, plus A3, X cubed, that is 10 to the cube. Do that for all of the 4 points. Okay, and then you will get what? 4 equation with 4 unknowns. Okay, 4 equation, 4 unknowns. It could easily be solved using algebra. 4 equation, 4 unknowns. In fact, we can use matrix in order to simplify the representation. So in a matrix form, we have the following representation. Okay, so in the first matrix, that this is the what? In the matrix 1, 10, 100, 1000. Those are the coefficient of the variable A0, A1, A2, A3. Okay, for the second line, 1, 15, 225, 3,375. Those are also coefficient. So all of these numbers in the matrix are coefficient of the equation. The variables here that we would like to know are A0, A1, A2, and 3, and represented by vector. Okay, vector is equal to the given velocity, 227.04, that is velocity at 10 seconds. For example, 602.97, that is velocity for 22.5 seconds. Okay, so we can use mathematics. Let me tell you, I am not going to review your previous mathematics. You have to review it yourself. You have to be prepared in this course. So you already know how to manipulate this or represent equations like this. So solving the 4 equation, you have to solve it. That is your assignment. Solve it. Solve the 4 equation. Your answer would be A1, A0, A1, A2, A3 with the following values. For example, what is the value that you will be solved in A2? A2 is equal to 0.13065. If not, you have to retry solving the matrix form. You can solve it any method you like, but matrix form is one of the easiest. That's why it is presented here. But you can solve it. There are several methods that you learn from mathematics, not only matrix form. Solve it for equation, for unknowns. That is the problem. Solving for equation. Of course, you already know how to solve for equation for unknowns. If you know how to solve 2 equations, 2 unknowns, you will you can solve 3 equation 3 unknowns, and therefore you can solve 4 equation 4 unknowns, and so on. A matter of what? A matter of repeating the procedure. Okay, and since we already know the coefficient of the direct fit polynomial, we can represent the discrete function in terms of an equation. We have an equation right now that could represent the discrete function, just like this one. We can find out what is the equation of this by using direct fit polynomial method. Okay, so the equation for the velocity is therefore, as given here, negative 4.3810 plus 21.289t plus 0.13065 t squared plus 0.005466 t cubed between t 10 up to t 22.5. That is only the valid domain. That is a valid region. Outside that, we do not know the equation. But inside that valid domain, we know the equation. We can estimate the equation by this direct fit polynomial. This is the beauty of this numerical method. Okay, it can be used in our daily lives, because in our daily lives there is no perfect curve. There's no perfect curve. If you want to find the equation of the curve, you can use this method. For example, there are discrete series of points, or a scatter graph. Okay, if you have a scatter graph, you can represent this. So this is one thing. So I have a module for analysis of curve using a scatter graph. You can search for that scatter graph under BSIE, managerial accounting. I have a module that explain scatter graph method. Also, I have a module that use high-low method of analysis. But in our numerical method, this is more precise, more accurate than those. Those are really scientific estimates also, but they are not as good as this one, because we are learning the best in this, the best technique here in numerical method. Okay, but still you need to maybe get the concept, get the principle, and therefore you have to search for that. I think this week I already uploaded those topics. Okay, I just search for that under the managerial accounting playlist. So look for it. So because we already have those points, so we can what? We can now create a curve that lines up all the 4 points that we use. It can line up all the 4 points that we use. The points at 10. So the green one, the blue one is the line, the curve. The green one is the discrete points. The green one is the discrete point. And we use 4 points. This 1, 2, 3, 4. Okay? 10, 15, 20, and 22.5. We use this. You can see here, it also uses 0 and the value at 30. Because we can solve for what is the value of this curve.
at time is equal to 0, you can put 0 here. Put 0 here, put 0 here. If time is equal to 0, the value is negative 4.3810. Okay? And that is not correct. Why? Because that is not under the valid region. Okay? The supposed value of our function at time is equal to 0 is 0. Okay? That's why it is very important to always consider the valid region. Okay? If you don't consider valid region, you will be misled. You will be misled. Okay? So this is a graph of our equation. So from 10 to 22.5, this is our direct fit polynomial. Okay? So therefore, the acceleration at time t is equal to 16 is given by. So taking the derivative of our direct fit polynomial, so we can what? Take the first derivative, we can have the equation for acceleration. Okay, it's a simple matter to take the derivative of this. So we'll have what? 21.289 plus 0.2613 t plus 0.016382 t squared. Valid between 10 and 22.5. But we can use this because our concern is 16. So 16 is between 10 and 22.5. Maybe not exactly at the middle, but it is along that valid region. So therefore, we can substitute t is equal to 16. So substitute it to this equation. We can find out that the acceleration is actually equal to 29.664 meter per second squared. This is our estimate. This is our estimate of the actual acceleration. Okay. Okay. This is our last slide for this module. Thank you for listening. Again, this is Dr. DrEYPEI, preaching engineering for nation building.